Hello, everybody. This is Professor Ma, and this is the section that we're going to talk about some results that comes out of integration by parts, and in particular, some formula we can derive out of integration by parts. Okay, and so here's integration by parts again, and we convert from the left-hand side to the right-hand side. And remember, the first thing is that somehow the problem we need to use integration by parts more than once, because when we take integration by parts, we place things with its derivatives. Okay, so for example, the integral of x squared ex, and if I do integration by part, and what happened is it knocked the integral down to a problem of square to x times e to the x. Okay, and if you do again integration by parts, then the x will be gone, then we will obtain our answers. We will wind up integrating e to the x. If we do it again. So then we landed and we know the answers. So if I put x to the third power up here, then I have to do it 3 times. First, I knock it down to x squared, then x, then I get the answer. Okay. And then you can probably think that, oh, then therefore for any power of x, I can do this 4th, 5th, whatever integer power. Further than that, I can do it with any sum and or multiple, and then I can do this for any polynomials. A 10th degree polynomials, I mean, a 3rd degree polynomial x cubed plus blah, 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 blah times e to the x dx. And I know I need to do it 3 times because that's when the last one will come out. The other square terms, like some other number times square terms, if you do it twice, you already come, the answer for that power comes out. Now, how do we organize these? Well, engineering, we used to teach these things we call tableau method. Come out of engineering school. Used to be that we calculate these. And so one recursive methods for doing this is set up this UDV as a table show, because we're going to take the derivative of the U, keep taking derivative of U, because we're going to apply integration by parts many times. Okay, so the U place the parts that being taken derivative, and then of course dV we're going to integrate to get V, then we're going to integrate it again and so on. Okay, and then we keep using integration by parts on the formula UdV, and it's going to be UV minus VDU, but we're going to replace that by another integration by parts and another integration by parts and so on and so on. And what does this do? This particular table basically gives you a way of organizing your work when we need to calculate a polynomial. Basically, you only work with polynomial times e to the some sort of that's easy to integrate, or something is easy to integrate the other components, sine or cosine, stuff like that. And we do it by having the polynomial parts that as u and keep taking derivative, and it's going to become 0. That's what the expansion stop. And the dv part, we keep integrating it. In this case, integral of e to the x over 2, okay, is twice, and we give it a constant 1/2, is 2 times the x. If we do it again, then that's going to be 4 times. Okay, do the 8 and so on. And this is enough for taking the integral. Why? Because now we can expand the original integral as, okay, multiply the diagonal, subtract well, or multiply this, since the signs already just plus that, plus and so on, until we get to the 0 times anything is 0, and it stops right here. Okay, because 0 plus 0, and of course the integration constants plus constants. Okay, so this is a table method for integrating polynomials. Then we can do the actual expansions. Okay. And notice with product e to the x, then the answer will have e to the x component, and usually the easier to do the simplifications, pull the e to the x portion out. Okay. It's useful for when we multiply polynomial to something integrate against something that is easy to integrate back and forth many times. Okay. And the second things we're going to do, use integration by parts, is to see some antiderivative formula for all the trigonometric functions. Actually, their power, any integer power. Okay, and we're going to deal with that later on, talk more about that. But okay, we're going to some of the algebra. We're going to simplify for S for sine, C for cosine of x, and T for tangent of x, just for simplicity's sake. Okay, and okay, we're going to basically talk about integral like cosine to the nth power, sine to the nth powers, and tangent, cotangent. Okay, let me remind everybody, the integral of sine, it's not with cosine of x. Okay, let me write as cosine of x dx is sine of x. That's a constant. Integral of sine of x dx is minus cosine of x plus a constant. Okay. How do we do integral of tangent of x? Well, we're going to treat tangent as sine over cosine, and we're going to set u to be cosine of x, and its derivative is going to be sine. And you wind up integrating 1 over u du. Oop, that's a u. Okay, so you wind up with log of u or log of cosine of x. Okay. And similarly for integral cotangent of x. Okay. Similar. Very similar. So then how do we integrate the secant and cosecant? The secant and cosecant are kind of integrating that is kind of strange. And it's a trick, involve a single trick, and as far as I know, it's only used here, only for secant and cosecant. Okay, and for secant of x, I multiply by secant x plus tangent x. I told you it's kind of, strange. I mean, it's very, clever. Whoever thought of this, okay, must have played around with the trigonometry for a long time. And if I multiply out in the top, it just happened to be tangent of x divided bottom secant x plus 10x. Okay. And the implication of this, derivative of secant is secant 10. Derivative of tangent is secant squared. In other words, if you do a substitution, and this is 1 over u du, and this is again log of u, and what's u? The u is secant x plus tangent x. It's worthwhile to remember these tricks. It's used once, okay? So you get these formulas, at least I know how to integrate secant of x. And similarly for integrating cosecant. So it's, you can check on the books and everywhere. I mean, the 6 trick functions, okay, how to integrate secant and cosecant, and these particular tricks. It tells you it's related to the log, okay. And now we're going to do higher degree integral of powers of these functions, and in particular we'll use cosine as a example. We're going to take the antiderivative cosine to the power when n is bigger than 2. And how we're going to do this? We're going to use integration by part. Okay. We're going to separate the cosine, one part u, one part dv. Right? I can take the derivative of the u, since cosine, it's pretty easy. And dv, since I'm integrating something, I can have to integrate something which I can integrate. In this case, cosine. So let me integrate that. Okay. This is the derivative of cosine to the m minus 1 power of the u. And of course, the antiderivative of cosine is sine. And apply this, use this to integrating by parts. U times v minus a plus v du. Okay. Now, the sine square itself, here comes the tricky part. Okay, the trick part is that very similar to the integration by parts, that we have to do it twice with the cosine and sine back and forth. This is very similar in algebra. Okay, basically the algebra is going to clean up, and what you wind up is you're going to have another copy of these. Join, so you wind up with 2 copies of these. Okay, and on the right hand side is whatever you have, then you can get the answers. Well, actually, n copies of that, not 2 copies. In last case, it's 2 copies. In this case, you get n copies. Okay. So we use the identity sine squared is 1 minus cosine squared. Then expand this integral into 2 integrals. One is integral of cosine. Notice its degree is smaller. We start out with the integral of cosine n dx. Now, one component now is degrees 2 degrees smaller. Okay, and the other components is the same as the original problem, because cosine squared times n minus 2 is cosine to the n. So we move these entire items to the other side, join the other side. Okay, become plus what? n minus 1 times the integral, plus on the left hand side original 1 copies, that's n copies of it. Okay, now I divide n below, and I get a what we call in mathematics a reduction formula. Why? Because this reduce calculating n power down to what? n minus 2 power. And n is a positive integer. So if I keep reducing it, it's kind of like a type of chain rule-like formulas. You know, keep doing it, and the power is smaller and smaller. Finally, it gets to a point where I can integrate. Okay, it gets to be first power or 0. So this is called a reduction formula. So this reduction formula came out of integration by parts. Okay, and so here's an example how we do that, and then the procedure become mechanical. You just plug in the number 5, and you just plug into the formula the number 5, and then goes along with the what and you do it for 3, because now it's integral 3rd degree and so on and so on. Okay. Similarly, a same trick used for antiderivative of power of positive power of integer power of S. So we get it. I let you check that. It works out exactly like cosine. Okay. In fact, this is a good test problem. Okay. It's nice to go through this algebra. Okay. How about for secant to the n? Okay. Okay. So for secant to the power n, okay, and again, we're going to separate the when n is bigger than 2. Okay, we're going to separate n bigger, secant square first of all itself tangent. Okay, so in this case n is bigger than 3, so we're going to separate out the 2 copies to the side dx. Okay, because I know what antiderivative of that is. That's tangent. So the derivative of secant square, I know what that is. It's the part dv I can integrate, and I can integrate secant square. Therefore, I set dv to be secant square, and v is equal to tangent. Now, use integration by parts. Okay, and so this will become secant to m will becomes. We will be in terms will be an antiderivative of secant n minus 2. And it continues, you get this formula. So it's very, so for integral of sine to the n and secant to the n, the algebra is very similar for cosine to the n. Okay, the ones you go through. So I'll leave up for you to check through the algebra. Now, the antiderivative of tangent and cotangent to the power n, we don't use the trick involves does not involve use integration by parts. Actually, using the substitutions. Okay, and basically what we do is we split out a square terms and we write a square as secant square minus 1. Why do we do that? Because we're going to use a substitution, and the derivative of tangent is secant square. That's why we split out the tangent square. So I get a secant square pops in. Okay, I can use that secant square. How? Oh, because now we separate this into 2 things. Okay, and first part is this is chopped down to integral power 2 less. Okay, so that's a part which we have to continue to work. But the front part, now I know what the answer is, because derivative of tangent is secant square. This part I use substitutions. Okay, use tangent square, so we use secant square dx. Okay, so the front part integral is du is replaced, dx replaced by du, the secant square cancel out, substitution. So it become a polynomial m minus 2. So then the antiderivative is m minus 1 divided by m minus 1. Okay, power m minus 1. U, of course, is tangent. So it's tangent m minus 1 divided by and these replace this from part. The minus 1, of course, the whole formula used to have a minus that portion. So this is the reduction formula for power of tangent. And for power of cotangent, it's the same thing. It almost runs exactly, except instead of using secant square minus 1, and for cotangent is cotangent is equal to cosecant square minus 1 plus cotangent square cosecant square. Yeah, cosecant square. Okay. So this is how we deal with antiderivative of all the tricks formulas and all their integer positive powers. Okay, so you should know how to derive as homework. Okay, You should know how to derive this form. Okay. That's it. Okay. Bye bye.